Okay, so now we want to move on to Lagrangian mechanics. So what is the idea in Lagrangian mechanics? Well, let me start off by drawing a space-time diagram. Okay. So here we have it. Our particle will move from some initial time, from some position, and it will land up at some final time, at some final position. Now, in Newton's mechanics, as we just saw, we have to specify two pieces of data, and it'll be the same thing here. We have to specify two pieces of data. In Newton's laws, we specified two initial conditions. Here, we're going to specify one initial condition. So the initial position, let's call that xi, and then we're going to specify a final condition. Let's call that xf. So look how different this is. We're specifying one piece of data now and one piece of data in the future. And then the particle will take some path between these 2 points. So let's call this blue path the path taken by the particle. So that's the path that moves along. However, now we have a bit of a puzzle, because that is one path linking the 2 points. But here's another path. Here's another path. So perhaps the particle doesn't take these red paths, but there are many different paths that we could draw. And what we could ask is, why does the particle take the path that it does? So let me tell you what Lagrangian mechanics tells us. The law of Lagrangian mechanics, in Newton's laws, there was a law. It was F is equal to ma. In Lagrangian mechanics, there's also a law. What the law is, it says the path taken by the particle minimizes the action S. Okay, so there's something called an action. If you plug a path into the action, you're going to get a number. And I'm going to have to tell you what the action is. And the actual path that the particle takes is the path that will give you the lowest value for the action. So now let me start off and tell you what is the action. So the action S is usually written as an integral. So this is an integral over time, dt, from the initial time to the final time of some other quantity L. Okay, so I've just introduced two new quantities. S is the action, and L is called the Lagrangian. And we'll make all of these very concrete very soon. And the Lagrangian, the only thing I'm going to tell you about it at this stage is that it depends both on x dot and on x. So both on the time derivative of x and on x itself. Okay, so what we want to do now is we want to derive an equation that we can solve for the path that minimizes the action. So what equation can we derive for a path that minimizes the action? Now, to motivate our approach, I want to remind you of something very simple, but I want you to have this very clearly in your head, okay? So let's look at some function f of x. Here it is. And f of x does something like this. It goes like this, then it goes like that, and it goes up again. Okay. So I can look at various points here. So let's say I'm looking at this point over here. So there's some position x, and let me consider a nearby point, which is x plus delta x, okay? There we go. What you can see is f went up just a little bit. So df is greater than 0. Let's pick a different point. Let's maybe consider a value of x somewhere over here. Okay? Now, x plus delta x will be just next to it. And what you can see here is df is less than 0. So if the function is decreasing towards the minimum, df is less than 0. If the function is increasing towards a maximum, df is greater than 0. But there'll be some point in the middle here where actually the function reaches its minimum, okay? It becomes tangent to this horizontal line. And if I pick a point of the function here, and I pick a neighboring point, so this is at the minimum, then df is equal to 0 at the minimum. So if you vary the position at the minimum, oh, sorry, it's just, I don't know why I put an E at the end of minimum. At the minimum, you find that df is equal to 0. And that characterizes the minimum. The fact that if you change the position slightly, the function doesn't change. That shouldn't surprise you too much. In fact, this is something that you know. Let's imagine we've got the function at the value of the minimum. Let's call that x minimum, so xm. And let's imagine that we add some tiny little delta x close to the minimum. If delta x is small enough, then we can just use a first-order Taylor approximation. And this is given by df dx at the minimum times by delta x. And if the value of the function doesn't change, which it doesn't at the minimum, it means that this term over here has to be equal to 0. Well, delta x is not 0, so we learn that at the minimum, df dx is equal to 0. And that's maybe the more natural way that you've seen it. You just take the function, you solve df dx is equal to 0. But for us, the nice thing is going to be delta s is equal to 0 for small changes about the path taken by the particle. Okay? Good. So this is the idea that we are going to use. So we're going to pick a path. We're going to look at small changes, delta x, around the path. And we're going to figure out for which path delta s is equal to 0. And that's going to tell us which path the particle takes. So let's now try to do that. So consider some path x of t and vary it. So I'm going to take x of t, and I'm going to replace this by x of t plus some little change, delta x of t, okay? In fact, let me introduce a little bit of notation that will probably be useful, I think. So x primed of t equals, so we're varying x of t into x primed of t. Now, the action depends on both x and x dot. So x dot of t will also vary. It will be x dot primed of t after the variation, and it will be x dot of t plus whatever change there is, delta x dot of t. Okay? Good. So let's maybe call this equation 1. Let's call that equation 2. And what I would like to do now is I want to know how is delta x dot of t related to delta x. And the way that I'm going to do it is I'm going to work out what is the time derivative of equation 1, and I'm going to compare to equation 2. So let's work out what is the time derivative of equation 1. Well, I will get d by dt of x primed of t, so that's just going to be x dot primed of t is equal to, I'm going to get d by dt of x of t, so that's just going to be x dot of t, and then I will also get plus d by dt acting on delta x of t. And now compare these equations. So if you look here, this term, x prime dot, agrees. So the left-hand side of 2 and our new equation agree. The first term on the right-hand side of 2 agrees with the first term on the right-hand side of our new equation. So those last terms must also agree, okay? So by comparing these two equations, so compare, what we learn is that delta x dot of t is equal to d by dt of delta x of t. Very good. That's what we wanted. Good. And we now would like to know, how do we pick x of t? So this is the central question that we want to learn. How do we pick x of t so that delta s is equal to 0? That's what we want to do. Great. We'll continue in a moment.